In the molecular modeling lab, we're going to see what some of these Lewis structures look like in 3D. You're going to use a model kit, and you're going to put together some of these molecular models. As you're doing that, in order to know how to put them together, you're going to have to draw out your Lewis structures, and we're going to get some practice with Lewis structures, steric numbers, and the molecular geometry. So, for example, let's look at the first one you're going to do, SiCl4. So let's think back to how we draw Lewis structures. So if we look at the periodic table, silicon has 4 valence electrons, and chlorine has 7 valence electrons. So 7 times 4 is 28 because we have 4 chlorines. And then 4 from the silicon tells us that we're going to have 32 electrons. So we have to think about which one's going to be our central atom. If we look at the periodic table, silicon is less electronegative than chlorine, which makes it more ideal for being a central atom since it's not going to pull the electrons towards itself. So we can put our silicon in the middle and our chlorines around it. And then we're going to give everybody their lone pairs. And then we are going to double check that we have the correct number of electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Which is exactly the number of electrons that we're supposed to have. So this is our Lewis structure for this molecule. So the steric number is the next thing we need in our table. So remember, steric number is the number of things bonded plus the number of lone pairs on the central atom. Okay, when we talk about steric number, we're referring to the central atom. So first we have the number of things bonded. So we have 1, 2, 3, 4 chlorines bonded. And remember, it's the things bonded, not the number of bonds. So even if there were a double bond here somewhere, we only have 4 chlorines bonded, so we can't count any of those more than once. And then we need to know the number of lone pairs. There are no lone pairs on the silicon. There are lone pairs on the chlorines, but not on the silicon, which is what we're focusing on. So we have 4 plus 0, which gives us a steric number of 4. And then we already said that there were no lone pairs on the central atom. So we're going to look at our molecular geometry table, and if you look in your lab handout, you will see that you have a molecular geometry table. So look up and tell me, what is the molecular geometry for a molecule that has 4 things bonded and no lone pairs with a steric number of 4? So I'm going to let you look that one up and tell me. And then the next thing I want you to do is to measure the bond angle between the atoms. So what you're going to do on your model kit, what I recommend doing is taking off 2 of the atoms and then try to measure the angle between the remaining 2. And you can also look at your molecular geometry table and tell me about what the bond angle should be between the between the atoms in this molecule. So let's do one more example here. Let's look at SeCl4. So we have, SeCl6. So if we look at SeCl6, selenium is in the group with oxygen, which means that it has 6 valence electrons. And chlorine, we know, has 7 valence electrons, There are 6 chlorines this time, so 7 times 6 is 42, plus, oops, that's 6, not 8. Plus 6 from the selenium, so that's a total of 48 electrons. So then we want to determine our central atom. Selenium is less electronegative than chlorine, so it has the higher bonding capacity. So let's put our selenium in the center, and we're going to put our chlorines around it. And then we're going to give all of the chlorines their lone pairs. So if we go through and do this, we have 2, 4, 6, 8 electrons times 6 chlorines is 48. And you can go through and count them up individually if you want to double check that. Now take a look here. How many electrons do we have around selenium? Remember, there are 2 in each bond, so we have 2, 4, 6, 8, 10, 12. And if you think back to the octet rule says that we can only have 8. So why can we put 6 chlorines, meaning 12 electrons around selenium? So if you think back to your video on Lewis structures, there are 2 criteria that we have to meet in order to exceed the octet on a central atom. And the 2 criteria for that are, number 1, we must have an atomic number, and we abbreviate atomic number as Z. We must have an atomic number greater than 12. So if we look at selenium on the periodic table has an atomic number of 34. So our first criteria is met. We have an atomic number greater than 12. And the second criteria is that the central atom must be bonded to a highly electronegative atom. And typically, the ones that we consider highly electronegative are fluorine, oxygen, and chlorine. So we're bonded to chlorine here, so our second criteria is met as well. But you always have to meet these 2 criteria in order to be able to exceed the octet on the central atom. Okay, if either of those criteria is not met, then you cannot exceed the octet on your central atom. Okay, so let's get back to our table here. So, what is the steric number for selenium here? So if we look at this, we have 6 things bonded to selenium. We have our 6 chlorines, and there are no lone pairs directly on the selenium. So, we have 6 things bonded and no lone pairs, which is a steric number of 6. So I want you to look up on your molecular geometry table and tell me, what is the molecular geometry for a molecule with a steric number of 6 that has 6 things bonded and no lone pairs? So I'll give you a second to look that up, and you're going to tell me what the molecular geometry is. And then the next thing that you need to do is measure your bond angle. And you can also double check on your table to see about what the bond angle should be. So you're going to complete the rest of the molecules on your table. You'll need to draw your Lewis structures, calculate your steric number, report the number of lone pairs, determine the molecular geometry, and you can use your table for that. You're going to draw the molecule in 3D, and then you're going to do the bond angles. So let's take a look at, really quickly here, how you would draw your molecule in 3D. So for example, if we go back to the silicon chloride, or SiCl4, if you make your molecule and then you hold it up so that you have as many things as possible in the plane, what you're going to find is that you have two of your chlorines in the plane. One of those chlorines is going to stick out towards you, and the other one is going to stick away from you. So the one that's sticking out towards you, you're going to put it on a wedge. And the one that's going away from you, you're going to put it on a dash. So to give you another example, let's look at the selenium chloride that we just did. So we're going to turn our molecule so that as many things as possible are in the plane. So if we do that, we should have our selenium and our chlorine. And then we're going to have one of our chlorines pointing out towards us, and one of our chlorines going away from us. Okay, so that's how you're going to draw your molecule in 3D. Anything that's in the plane goes on a straight line. Anything that's pointing towards you goes on a wedge, and anything that's going away from you goes on a dash. So, you're going to fill in the rest of your table and build these models. So make sure that you have read through your lab handout and that you have done and submitted the purpose and procedure for your lab notebook. And I will see you in lab.